Okay, hello everyone. I'm Chen Xi, and I'm a PhD student at in this UTA at Mathematics Department. I'm Dr. Liu's PhD student, and today I'm going to talk about the Liutex dynamics based on matrix governing equation for incompressible flow. Give me a second. Uh, okay. So first, I'm going to recall what I have said in the conference, but in about the matrix equation. But in this case, we only talk about 2D case, and I will talk about the steps to solve it numerically, and I will also talk about the Liutex and the resistance in 2D incompressible flows. And after that, I will talk about how to take finite differences with matrices. And after that, I will give me a second. Uh, and after that, I will talk about the initial conditions and the boundary conditions for my simulation, including that for the velocity and pressure. And after that, I will display my result and talk about some conclusions. So again, this is the matrix governing equation. And here this U is the velocity gradient matrix, nebula V, and P is the pressure matrix. It is 1 over density rho and formed by the terms of second order derivatives for pressure. And we let U equals to A, B, C, negative A. Here A stands for partial U over partial X, and it is also for negative partial V over partial Y, because this is an incompressible flow. And B stands for partial U over partial Y, and C stands for partial V over partial X. And here the pressure matrix P, we have second order derivatives for this P, and this P stands for normalized pressure, which is the pressure over density. And since the trace of the velocity gradient matrix U is 0 for incompressible flows, thus the trace for d over dt of U minus nu Laplace of U, it is also 0, which means the trace of U squared plus P should be 0. And we plug in the formula I gave for U, which is A, B, C, negative A. We multiply them, we got U squared equals to A squared plus BC times identity. And thus we have Pxx plus Pyy, which is the two elements on the diagonal of P matrix. That plus 2 times A squared plus BC should be 0. Hence, we got a Poisson's equation for this normalized pressure P, Laplace P equals to negative 2 A squared plus BC. And now let's talk about how to solve it numerically. And we'll just let P and N denotes the subscripts denotes the past, previous time step, and the next time step. And we can get the A, B, and C for the next time step through these time matching equations. D over dt of A minus nu Laplace of A plus Pxx plus A squared plus BC that equals to 0. D over dt of B minus nu Laplace of B plus Pxy equals to 0. D over dt of C minus nu Laplace of C plus Pxy equals to 0. Here we can notice that the second and the third equation are identically the same for B and C. That is because C minus B is the vorticity, which satisfies the vorticity transport equation. So d over dt of C minus of vorticity minus nu Laplace of vorticity, that should equals to 0. And after that, we can get the value for pressure and U and V for the next time step by using the Poisson's equation. Laplace P equals to negative 2a squared plus bc. Laplace U equals to partial A over partial X plus partial B over partial Y. That is because A is partial U over partial X and B is partial U over partial Y. And similarly, Laplace V equals to partial C over partial X minus partial A over partial Y. Now I'm going to talk about the Liutex and resistance. So the idea of resistance was developed by me 2 years ago, and we published it in last year. Now we are talking about, it was designed for 3D flows. Now let's talk about how to simplify this formula for 2D cases. Again, we start from A, B, C, negative A for the velocity gradient matrix. And in the principal coordinates, we can transfer it to the principal coordinates through a special orthogonal transformation. It will look like 0, negative r over 2, epsilon plus r over 2, 0 for rotational point, or 0, L over 2, epsilon plus L over 2, 0 for non-rotational point. And here L stands for the resistance, R stands for the Liutex, and this epsilon stands for the shear. And we know that through the orthogonal transformation, the magnitude of the vorticity is preserved. Thus, the absolute value of C minus B, it should equals to epsilon plus R over 2 minus negative R over 2, which is epsilon plus R, that is for the rotational points. And for non-rotational points, that should equals to epsilon plus L over 2 minus L over 2, which is just the epsilon. And therefore, let's look at the number on the lower left corner, epsilon plus R over 2, that equals to the absolute value of C minus B minus R over 2. And the epsilon plus L over 2 equals to the absolute value of C minus B minus negative L over 2, which means we can put them together by using a uniformed variable. Negative resistance stands for both for negative resistance for non-rotational point, but it also stands for Liutex for rotational point. So we use this board, negative L, which is Liutex and negative resistance together. Then the principal matrix should look like 0, negative of negative L over 2, and C minus the absolute value of C minus B minus negative L over 2, 0. And the determinant of the matrix also preserved through the special orthogonal transformation, which means negative A squared plus BC should equals to negative L over 2 times the absolute value of C minus B minus negative L over 2. And we notice this is a quadratic equation for the negative L, and we can solve it and get the formula for negative L. It equals to the absolute value of C minus B minus square root of C plus B squared plus 4A squared. So this formula, I get it from the simplification of Liutex and the resistance, which we developed for 3D. But it is first published by Kola in his paper in 2007. And in his paper, he referred it as the vorticity residue. So, which means in some sense, we agree with each other in the 2D cases. Now I'm going to talk about how to take finite differences with matrices. And the reason I want to talk about this because nowadays MATLAB and Python are very popular for programmers, and this type of language are matrix-based language, which means if you multiply two matrices together, it will be faster then you write a loop with a 2-layer loop with exactly the same calculation. And the numerical formula for the first order derivative with fourth order of accuracy is f prime of x naught equals to 1 over h 1 over 12 f of x naught minus 2h minus 2 over 3 f of x naught minus h plus 2 over 3 f of x naught plus h minus 1 over 12 f of x naught plus 2h. So the coefficients for these 5 numbers is 1 over 12, negative 2 over 3, 0, 2 over 3, negative 1 over 12. Thus, we can get the first order derivative for a function with n grid points by multiplying it with n by n matrix on the right, and this n by n matrix have 5 diagonals. In the middle we have 0, and then we have 2 over 3 beneath that, and we have negative 1 over 12 beneath that, and above 0 we have negative 2 over 3, and we have 1 over 12 above that. And we can also apply this matrix to n by n function, and by doing that we are just repeating what we did on each row for each row. And then this derivative is actually a partial derivative on x. So partial f over partial x equals to the values n by n matrix times the derivative matrix n by n matrix. And similarly, we can use the matrix to find the partial derivative on y. So we can transpose this matrix from n by n to n by m, so we change y into x, and then we can multiply n by m matrix on the right, and then transpose it back. And then we can find it is equals to the transpose of this n by m matrix and the time f of n by n, but on the left. And since this matrix is antisymmetric, this equals to negative n by m matrix times f of n by n. And similarly, we can get the finite difference second order with another matrix. And the formula we have is 1 over h squared negative 1 over 12 f of x naught minus 2h plus 4 over 3 f of x naught minus h minus 5 over 2 f of x naught plus 4 over 3 f of x naught plus h minus 1 over 12 f of x naught plus 2h. So this second order derivative matrix, let's call it S n by n, it's still 5 diagonals. In the middle, we have negative 5 over 2, and above that and beneath that, we have 4 over 3. And above the 4 over 3, we have negative 1 over 12, and beneath that, we have negative 1 over 12. And this matrix now is symmetric, which means we just multiply it on the left for second order derivative on y, and on the right for second order derivative for x. And now let's talk about the simulation I have, and the x and the y ranges from negative 10 to positive 10. And on the x-axis, I put 2 lambda ocean vertices, and one of them is at negative d0, and the other one is at d0. The grid resolution I pick is 128 by 128, and because we are using the derivative formula with fourth order accuracy, which requires us to provide the boundary with 2 grid points layer thick on the outside. And the time step I pick is 0.004, and totally we have 10,000 steps. And the time matching scheme I use is the Craig-Nicholson method. And here, this is the exact solution for this lambda ocean vertex. And in the cylindrical coordinates, Vr equals to Vz equals to 0. And V theta equals to gamma over 2 pi r, 1 plus e to the negative r squared over 4 nu t. Here, gamma is a constant for circulation, and the nu stands for the kinematic viscosity. And for the pressure, partial p over partial r equals to the density rho times v squared over r. And now let's just pick gamma equals to 2 pi and t equals to 1 and the nu equals to 0.25. And we can get the formula for Lambda-Ocean vortex for u and v. So uO equals to 1 over e to the negative r squared over r squared times negative y. And VO equals to 1 minus e to the negative r squared over r squared times x. And the pressure, I just integrated from the velocity square over r, and we got PO equals to ln of r squared plus E1 of negative 2r squared plus 2E1 of negative r squared. Here E1 is the exponential integral function. And for the initial condition, for the velocity field, we just use uOx minus dy and uOx plus dy and add them together. And the same case for v component, vox minus dy plus vox plus dy. However, for pressure, we need to, because u and v, we can just add them together, but that doesn't satisfy Laplace p equals to negative 2 of a squared plus bc. So we need to solve the Poisson's equation to get the initial condition. And for the boundary condition, I just set the fixed boundary with the initial values of the exact solution, and then times it with decreasing coefficient, which is e to the negative 2 alpha t. So we have pressure at the boundary, it equals to PO of x minus dy plus PO of x plus dy times e to the negative 2 alpha t, and the same formula for u and v. And totally we have, I calculated 2 cases, and on the first case on the left, these 2 vertices are put on negative 1, 0 and positive 1, 0. And on the, so d equals to 1. And on the second case on the right, d equals to 2, we can see these 2 vertices are slightly stay away from each other. And the background color stands for the Liutex magnitude. And this arrow stands for the velocity direction, and the color of these arrows stands for the magnitude of the velocity. Now let's look at the first case. So we can see these 2 vertices just combine together and in the center, and then there are some dissipations after that, but it is totally different for the second case. And we can see that these 2 vertices rotated, but they are not combining together. For example, at here or here, maybe just here. So they just never combine together. And the how I explain this is like, let's look at the resistance. So here I also put the resistance on my figure, and let's look at the first one. So we can see at the beginning, all this resistance is on the outside of the vertex, and there's no resistance between these two vertices. However, on the second case, we can see that there is resistance in the middle, and we can see as time passes, this resistance is just staying in the middle like a barrier blocking these two vertices from meeting each other and prevent them from merge into one vertex. Okay. So my conclusion for this is the Liutex dynamics can be developed based on the matrix governing equation because Liutex can be found explicitly through an algebraic equation from the velocity gradient matrix. And this combination of two co-rotating vertices may be affected by this resistance, since resistance is the continuous extension of Liutex from rotational point into the non-rotational point. It is possible for it to serve as an impediment for Liutex to pass through. And for my future work, we can also develop the simulation for 3D flows, since turbulence can only be generated in the 3D environment. And we can also develop the matrix governing equation for compressible flows. So far that one is just incompressible flow. So for compressible flow, it has much more applications in real life, such as in atmospheric science and other fields. And that is my presentation.